So we spent a long time talking about solutions and aqueous-based solutions, and now we have to turn our attention to a very critical consideration, and that is the self-ionization of water. You see, whether you're talking pure water or water as a solvent in a solution, some of the water molecules self-ionize. They dissociate into protons and hydroxide ions in a 1-to-1 ratio. Of course, it's very limited, and not all the water molecules in a glass of water are in their ionic form. As a matter of fact, the overwhelming majority remain as water molecules. But there is nevertheless a small amount of proton and a small amount of hydroxide in a glass of pure water. Same is true in any aqueous solution where water is present. And of course, if our definition, Arrhenius definition of an acid, is something that dissociates in water to produce protons, well, it looks sort of like water is behaving as an acid in this equation. But of course, our Arrhenius definition of a base is a substance which in water dissociates to produce hydroxide. So since water is self-ionizing and producing both, is it an acid or is it a base? Well, the answer lies in the balance of the two. And if pure water produces one of each ion for each water molecule it dissociates, there's a perfect balance in protons and hydroxide ions. And therefore, with even concentrations of both, namely when proton concentration equals hydroxide concentration, then the solution is neutral. And yes, pure water is neutral. It has even numbers of both ions. Now, another important fact to remember always is for any water-based solution at 25 degrees C, the product of these two ion concentrations is always going to equal 10 to the negative 14th. That's a critical understanding, because if you know the proton concentration in the solution, you'll be able to calculate the hydroxide concentration, and vice versa. If you know either concentration, you can find the other by virtue of this simple relationship. Now, what about pure water itself? Well, we're going to produce equal amounts of both ions in pure water. We don't know what that concentration is, but let's call it X. So water will dissociate and produce X moles per liter of protons. Well, since it dissociates in a 1-to-1 ratio, it should also produce X moles per liter of hydroxide. And if we take X, concentration of protons, multiply by X, concentration of hydroxide, and set it equal to 10 to the negative 14th, that means X squared equals 10 to the negative 14th. And when we solve for X, which could be either concentration, they're the same here, you get 10 to the negative 7th molar. In other words, both proton and hydroxide concentrations in pure water are the same, 10 to the negative 7th moles per liter, which is very small. That's a 10 millionth of a mole per whole liter of water would be the number of moles of protons and hydroxides. Very small. Now, more importantly, a very important thing happens if you're not talking pure water. Let's say instead we add some hydrochloric acid to our pure water. Then things change completely, because if we're asked in a 0.0100 molar solution of hydrochloric acid, what is the proton concentration? Well, since hydrochloric is a strong acid and therefore completely dissociates into protons and chloride ions, if you have 1/100th of a mole per liter of hydrochloric acid, then you will have 1/100th of a mole per liter of protons. So we can say the proton concentration is the same as the strong acid's concentration in this problem. Now, what does that make the hydroxide concentration? Well, if you remember, the proton concentration, whatever it is, times the hydroxide concentration must be constant, 10 to the negative 14th. And therefore, in this 0.01 molar acid solution, you could calculate the hydroxide concentration by simply dividing 10 to the negative 14th by 10 to the negative 2. And you will get a hydroxide concentration of 10 to the negative 12 molar. In other words, there's an imbalance here. If you have all of this proton in the solution, but you only have a millionth of a mole per liter of hydroxide, the imbalance is definitely in favor of the protons. Far more proton than hydroxide. That's what defines an acid solution rather than a neutral or basic solution. That would be a greater concentration of protons than hydroxide ions in the solution. Now, if we want to think the same way, only in terms of a basic solution, we know that sodium hydroxide is a very strong base. It's highly soluble. It completely dissociates into sodium and hydroxide ions. So, of course, if you have 0.2 of a mole per liter of sodium hydroxide, you're going to have 0.2 of a mole per liter of hydroxide. And that would be our concentration of hydroxide ions. How would you find the proton concentration? Well, I know that whatever it is, the product of it and the hydroxide concentration has to equal 10 to the negative 14th. And therefore, if I divide 10 to the negative 14th by 0.2, I get a proton concentration of 5.00 times 10 to the negative 14th molar. So I reiterate, because the product of these two ion concentrations is always a constant, you can always find one if you're given the other, and vice versa. But my warning would be, if God gives you lemons, make lemonade. Focus your attention on hydroxides if you're talking about a basic solution, and focus your attention on proton concentrations when you're given an acid solution. Don't try and think about hydroxide in an acid solution until after you determine the proton concentration. Then you can start talking about hydroxide concentration. And of course, once again, recognize this is a very small number of protons compared to a relatively large concentration of hydroxide ions. And in this case, hydroxides outweigh protons, which of course makes the solution basic, the abundance of hydroxide versus protons. Now, when we start playing this game, since the product of the two concentrations is always very small, we end up dealing with exceedingly small numbers. It's hard to wrap your mind around 600 millionths of a millionth of a liter, mole per liter, we should say. And that's why scientists have developed what's called the pH and the pOH scale as nothing more than a different way to represent the proton concentration, pH, or the hydroxide concentration, pOH. And very simply, the pH is essentially just another way to express proton concentration. You take the negative base 10 log of that proton concentration. And of course, a log is nothing more than the exponential value of the base, and in this case it's base 10. So if I were looking at, say, this first problem, and I wanted to know the pH of this solution, well, since the proton concentration is 10 to the negative 2, the log of 10 to the negative 2 is negative 2, and if I change the sign, make it negative, I get a pH of 2. That's easy enough, especially when you have powers of 10. Likewise, the pOH of a solution is nothing more than a fancy way to express the hydroxide concentration. Negative log of hydroxide concentration. So if I know the hydroxide concentration in the solution is 10 to the negative 12th molar, the log of that is negative 12, and the opposite of negative 12 is a pOH of 12. Now, please notice how these numbers change as we go from neutral to acidic to basic. And that is because, if you'll remember, when we looked at simply pure water, both concentrations were 10 to the negative 7th. So that means the pH would have had a value of 7. Log, negative 7, opposite of log, 7. And the pOH of a neutral solution, pure water, is also 7. Now look what happened here when we threw acid into the solution. Look what happened to the pH. It actually went down. That's right, that's something you've got to remember, and it's difficult when you first start, that if the concentration of protons increases, then the opposite of its log actually decreases. So any pH less than 7 is representing an acid solution. Likewise, any pH greater than 7 means that this value of protons is 10 to the negative 8th, negative 9th, negative 10th. We get negative logs greater than 7. But we'd have those because the hydroxide concentration is going up, driving the proton concentration downward. So this would have to be a base. So pH is greater than 7, basic. pH is less than 7, acidic. So how about in this case? What's the pH of this solution? Well, same thing. You grab your calculator and take the negative log of 5 times 10 to the negative. And we get a pH of 13. It's running off the sheet. 13.301. A very high pH, to be expected for a very strong base. And if you want to know the pOH of the solution, you'd take the negative log of the hydroxide concentration. And it comes out to 0.699. Very small value for pOH, meaning very high concentration of hydroxide, very basic. Now, interesting thing, if you take the pH of the solution, 2, and you add it to the pOH, 12, you get 14. Same thing here, take the pH of the solution, 13.301, add it to the pOH, 0.699, you get 14. And that should make sense because, after all, if proton concentration times hydroxide concentration always equals 10 to the negative 14th, well, in mathematics we learned that if you perform the same operation on both sides of an equation, it remains an equation. So let's take the negative log of this side and the negative log of that side. And the negative log of the proton concentration is what we call pH. The negative log of hydroxide concentration is what we call pOH. And of course, when you multiply exponential numbers, and these logs are exponents, you end up adding the exponents. So that means pH plus pOH should equal the negative log of 10 to the negative 14th. In other words, 14. So if I give you any one of these 4 things, a pH, a pOH, a proton concentration, or a hydroxide concentration, you should be able to find the other 3 fairly easily. Given a concentration of either one, divide it into 10 to the negative 14th, you'll know the concentration of the other. And if you're given a pOH or a pH, simply subtract it from 14, and you'll know the pH or pOH of the other thing you were not given. Very simple. In the next video, part 2, on self-ionization of water, we will look at some slightly more involved problems.